Imagine a construction crew operating some really heavy machinery right near your primary data center.
Oh boy, I know where this is going.
Yeah. And in an instant, they accidentally sever the main fiber optic cables, the exact ones connecting your primary site to your secondary disaster recovery site.
That is pretty much a textbook nightmare scenario right there.
It really is, because both of those physical data centers are actually perfectly healthy. I mean, power's flowing, the servers are humming along.
Right, but they are now completely blind to each other.
Exactly. So in a matter of milliseconds, your storage architecture has to make this incredibly complex, automated decision, one that will either completely save your enterprise data or trigger a catastrophic split brain scenario where your applications basically just tear themselves apart.
Yeah, and that is exactly the kind of high-stakes architecture we are looking at today. Welcome to the deep dive, everyone.
We have a highly focused, really critical mission today. We are prepping for the NS0-165 exam, and if you are going after this certification, you know the massive amount of architectural ground we have to cover.
Oh, absolutely. This is a massive amount of territory.
We are talking storage platforms, core on ONTAP Storage, networking, storage protocols and connectivity, data protection, security, and of course, performance.
Right, and to respect your time, we are setting a pretty rigorous, fast-paced tone today. We're going to dissect 10 critical practice questions drawn straight from those core domains.
But we aren't just giving you the answers to memorize, right?
No, we are going to extract exactly why the correct answers work at a really mechanical level. We want to equip you with the underlying architectural logic.
Yeah.
You need that to actually understand the system, which is what ultimately guarantees your success on the exam.
I love that. We are building foundational intuition here. So let's just jump right into the first major concept. This one centers on storage efficiency and security.
Okay, let's hear it.
On the exam, you will see a question asking, which encryption technology allows for data deduplication efficiency to be maintained across multiple volumes within the same aggregate?
Right, and the test is going to try and bait you here. They will throw in options like volume-level software encryption or maybe external hardware disk encryption.
I think they even throw in standard clear text sometimes, just to test your baseline knowledge. But we know the correct answer is C.
Yes, the correct answer is C, aggregate-level software encryption.
Okay, so I really want to visualize this because it is a crucial mechanical concept. If we encrypt at the volume level, we are scrambling the data before the underlying system can actually look for duplicates, right?
Exactly, just see scrambled noise.
So doing it at the aggregate level, is that basically like wrapping a massive shipping pallet in opaque, impenetrable security film rather than individually wrapping all the tiny boxes stacked on top of it?
That is a really great physical analogy.
Because you secure the outer perimeter so the internal system can still organize and sort the boxes inside.
Yeah, to understand exactly why this works, you have to look at where the encryption is physically applied in the storage stack. NetApp storage encryption at the aggregate level, it encrypts data at the absolute foundation.
Which sits logically below the volume layer?
Right, precisely. Because the encryption happens underneath, the ONTAP operating system can still clearly analyze all the raw data blocks residing up at the volume level.
Oh, okay, so it can identify blocks that are perfectly identical across multiple different volumes as long as they are within that exact same aggregate.
You got it. It then performs the deduplication, stripping out all those redundant blocks. That saves immense amounts of physical disk space, while ensuring your data at rest remains strictly encrypted against any physical theft.
That makes total sense. So once we have that data efficiently stored, deduplicated and properly encrypted, we obviously need to protect its state over time.
Which leads us directly into how we manage backups.
Right. So the exam asks, which two settings are primarily defined within a standard snapshot policy in ONTAP? Now, the distractors here usually involve the physical location of the disaster recovery site, or maybe the specific encryption algorithm being used.
But we are really just focusing on the automated schedule here.
The correct answer is A, D, the maximum number of copies to retain and the frequency at which copies are automatically created.
Exactly.
But here is where I need some clarification from you, because ONTAP snapshots are famous across the industry for being incredibly space efficient. I mean, they only capture block level pointer changes, right?
Right. They absolutely do not duplicate the entire file payload.
So if they are so tiny and efficient, why do we even need a retention limit? Why can't we just keep every single snapshot forever?
Well, because in an active enterprise environment, even highly efficient metadata eventually consumes significant physical space. Think about it. Every time a user modifies a file, new blocks are written, and the snapshot locks the old blocks in place.
Oh, right, so they pile up.
Exactly. If you have unrestricted snapshot growth, you will inevitably exhaust your physical storage capacity. And that is exactly why a formalized snapshot policy is mandatory.
Because it automates your protection strategy.
Yes, by enforcing two strict parameters. First is the frequency. This defines the exact cadence, like hourly, daily, or weekly, at which the snapshots are triggered.
And the second is the retention limit.
Right. That sets the absolute maximum numerical limit of copies to keep. Once your system hits that limit, ONTAP automatically deletes the oldest snapshot copy to make room for the newest one.
Which prevents the system from just suffocating itself. That makes perfect sense. So deleting old snapshots saves space. But we also have actual active data that eventually cools down over time.
Oh yeah, retaining older data locally on high-performance drives gets incredibly expensive very fast.
We have to figure out where that inactive data goes. So the exam covers this by asking, in a FabricPool environment, what type of data is automatically moved from the performance tier to the cloud tier by default?
And they will try to trick you with things like system configuration files or recently written backup data. But the correct answer is A.
Yeah, the correct answer is A, inactive data blocks that have not been accessed for a long time.
Right.
You know, I always compare this FabricPool mechanism to a really highly efficient smart closet in your house.
Okay, I like where this is going.
Yeah, so when the summer rolls around, you take your heavy, bulky winter coats and you move them up to the attic. And that attic represents our cloud tier.
Exactly.
That automated action frees up the premium space in your main bedroom closet, which is your performance tier, for all the everyday clothes you're actively wearing right now.
That perfectly captures the automated tiering logic. I mean, FabricPool is designed to constantly monitor the temperature, or essentially the access patterns, of data across your aggregates.
So it's always watching to see what is being used.
Yes. When it identifies specific blocks of data that haven't been read or written to for a predefined period, it officially flags them as cold, inactive blocks.
And then by default, it physically extracts those inactive blocks out of your highly expensive, high-performance local SSD tiers.
Exactly right. It automatically tiers them down to lower-cost object storage, something like an AWS or Azure cloud environment.
Which means you drastically reduce your overall data center footprint and infrastructure costs.
While ensuring your active, hot data retains all the ultra-fast local performance it requires.
It's brilliant. But pushing all that data around, whether it is hot or cold, relies entirely on a highly stable network, which brings up a really counterintuitive networking concept from the exam.
Oh, the SAN logical interface question.
Yes. The exam asks, what is the expected behavior of a SAN logical interface during a storage node failure in an HA pair?
The options here strongly suggest that it automatically migrates to a physical port on the partner node, or maybe that it changes its network address. But the correct answer is B.
Right. The correct answer is B. It remains associated with the failed node and goes offline. See, this is where my intuition completely fails me. If a storage node completely crashes, why wouldn't the network interface just automatically migrate over to the surviving partner node to keep the data flowing? I mean, that is exactly what NAS data logical interfaces do.
It is, but it's a fundamental architectural difference in how these protocols are engineered to operate. NAS protocols like NFS and SMB are actually designed to tolerate brief network dropouts.
So they will happily follow an IP address if it moves to a new physical port on a surviving node.
Exactly. SAN protocols, on the other hand, operate at the block level. They require strict, predictable, and dedicated paths.
Oh, I see.
Therefore, SAN logical interfaces, or SAN lifts, absolutely do not automatically failover. They stay permanently tied to their home node and simply go dark when that node fails.
Wow. Okay, so it is entirely the responsibility of the host server's multipathing software to instantly detect that the primary path is dead.
Yes. And then that software seamlessly routes the storage traffic through other pre-established available network paths to access the data.
Okay, so the host multipathing handles a local single node failure perfectly. But let's go back to that disaster scenario we started the deep dive with. What happens when an entire geographic site goes down?
Right, the MetroCluster scenario.
Exactly. The exam asks, which two components are necessary for implementing a synchronous replication solution in a MetroCluster IP configuration? The options will throw in physical tape libraries or third-party cloud gateways.
But the correct answer is B, C.
Yes, the correct answer is B, C. high-speed backend switches for cluster traffic, and a software-based mediator for automated failover monitoring.
Exactly.
So I fully grasp why we need the backend switches for the heavy data replication, but why is a separate software mediator strictly necessary here? Shouldn't the two geographically separated clusters just talk to each other directly over those backend switches to know if the other one is functioning?
Well, they do communicate directly over those links, but that direct connection is the exact reason the software mediator is so critical. Think back to your construction crew scenario earlier.
Right, where the cables got cut.
Exactly. If the fiber optic cables connecting Site A to Site B are completely severed, both physical sites are perfectly healthy, but they can no longer communicate.
Oh, so if they only relied on direct communication, Site A would assume Site B was destroyed and attempt to take over,
Yes, and Site B would assume Site A was destroyed and also attempt to take over.
which creates that catastrophic split-brain scenario where both sides try to write conflicting data simultaneously, completely corrupting the applications.
Precisely. That is why the mediator sits in a third, physically independent location. If the sites lose contact with each other, they instantly check in with the mediator.
Ah, so the mediator acts as the definitive tiebreaker.
Exactly. It safely orchestrates an automated failover, ensuring only one site remains active and your data stays perfectly intact.
Okay, that prevents physical site disasters flawlessly. But modern infrastructure is constantly under attack from active malicious disasters too, like ransomware.
Oh, absolutely, which is heavily tested.
Yeah. The exam tests this by asking, when Autonomous Ransomware Protection is active, what is a primary action taken by ONTAP if it detects a suspicious surge in data entropy?
And the options might suggest shutting down the entire storage cluster or maybe deleting recently modified files. But the correct answer is D.
The correct answer is D. It creates a protective snapshot to act as a recovery point.
Exactly right.
I find this feature so brilliant. I view it like an advanced smart fire alarm system in a high-end art museum. It doesn't just ring a loud bell when it detects smoke. It instantly drops a heavy, fireproof blanket over your most valuable paintings the exact millisecond the smoke hits the sensor.
That is a really exact representation of the storage mechanics at play here. But to fully comprehend this, we must define data entropy.
Right. What is entropy in this context?
Entropy refers directly to the level of randomness or unpredictability contained within a file. Normal user files, like your spreadsheets or Word documents, have highly predictable standard structural patterns.
But ransomware operates by rapidly encrypting your files.
Exactly.
Yeah.
Which fundamentally scrambles them and spikes their randomness, their entropy, to near maximum levels. Autonomous ransomware protection is constantly monitoring your active storage workloads for these exact behavioral patterns.
So if it detects a sudden, suspicious surge in data entropy, it doesn't just send an email and wait for a human administrator to investigate.
No way, that would be too slow. It immediately triggers an automated protective snapshot copy.
Which locks your data state at that exact moment.
Right, providing an instant, clean, and immutable recovery point before the malicious encryption can spread any further into the file system.
Having that fast, automated defense is such a massive advantage, but managing all these security alerts, the tiering policies, and snapshots across a massive enterprise, that can get chaotic quickly.
Oh, it gets incredibly complex, which is why centralized management is heavily tested on the exam.
Right. So the question is, which platform is primarily used to deploy, manage, and monitor Cloud Volumes ONTAP instances across different cloud providers? The test will offer distractors like physical system service processors or local desktop consoles.
But the correct answer is A.
The correct answer is A, the Blue XP management interface.
Yes.
Now, my major question here is about administrative workflow. If a large enterprise is already spending millions of dollars using AWS or Azure, why wouldn't a storage administrator just use the native management dashboards provided by those specific cloud vendors to manage their storage?
Well, the core issue there is operational fragmentation. Modern enterprise infrastructure environments are rarely confined to a single monolithic cloud provider anymore.
That's true. It's a multi-cloud world now.
Exactly. You might run your active customer databases in AWS, your disaster recovery protocols over in Azure, and maybe dedicated analytics workloads in Google Cloud.
Oh, I see. So if you rely strictly on native vendor dashboards, your administrators have to constantly log in and out of entirely disconnected cloud silos.
Right. They would have to master 3 different management paradigms and APIs. BlueXP eliminates that operational friction entirely. It serves as a unified cloud management platform.
So it allows administrators to deploy, configure, and seamlessly monitor Cloud Volumes ONTAP instances across all major public cloud providers.
Yes, all from one single centralized location. It completely normalizes the management experience regardless of where the data actually lives.
That is huge for efficiency. And whether you are managing that data up in the cloud or down in an on-premise data center, your application performance relies heavily on how the data is physically distributed.
Absolutely.
The exam addresses this by asking, what is the primary benefit of utilizing the rebalance function on a FlexGroup volume?
The incorrect options usually talk about migrating data to slower tiers or encrypting it with new master keys, but the correct answer is D.
The correct answer is D. It redistributes data to ensure even capacity usage across all members.
That's it.
You know what this mechanical process reminds me of? Loading a massive ocean-going cargo ship.
Okay, lay it on me.
A FlexGroup volume is like the entire ship, and the rebalance function acts as the highly trained loadmaster. If you stack all the heavy shipping containers strictly on the left side of the vessel, the boat lists heavily, creates massive drag in the water, and slows down to a crawl.
Right, it ruins the performance of the ship.
Exactly. So the loadmaster shifts the containers around so the weight is perfectly even, allowing the ship to cruise at maximum speed.
That physical analogy mirrors the underlying storage mechanics perfectly. Because a FlexGroup volume is not just one simple container. It's a massive, unified namespace that physically spans multiple constituent volumes, which are known as members.
And those are distributed across different physical hardware nodes, right?
Exactly. When you first provision it, the data is perfectly balanced. But over months or years, as millions of files are added, modified, or deleted, the data footprint naturally becomes uneven.
So one constituent member might fill up to 90% capacity, while another sits completely idle at 10%.
Yes. And that full member becomes a severe performance bottleneck for the whole system. The rebalance function dynamically and physically moves files and directories among those constituent members in the background.
Which guarantees even capacity usage across the entire cluster.
Exactly. It prevents any single node from being overloaded and maintains peak performance for the client.
Optimizing that internal distribution is clearly crucial, but it has to link directly to external network transport capabilities to ensure end-to-end speed.
Right, the network protocol matters a lot.
The exam explores this shift by asking, which transport protocol is used when implementing NVMe storage services over an existing standard Ethernet network infrastructure? The options will definitely try to trip you up with Fiber Channel Protocol or serial-attached SCSI.
But the correct answer is B.
The correct answer is B, NVMe over TCP. I have to admit, I am a little confused by the engineering choice here. I mean, NVMe is all about unlocking blistering, ultra-fast read and write speeds. Why on earth would a large enterprise deliberately choose TCP over building out a dedicated, specialized fiber channel infrastructure for their high-speed NVMe storage? Doesn't Ethernet inherently bottleneck the performance?
It is an excellent architectural question, and it fundamentally comes down to balancing ultra-high application performance with realistic infrastructure economics.
Okay, so it's a cost thing.
Mostly, yes. Traditionally, running high-end block storage absolutely required deploying Fiber Channel. And Fiber Channel is incredibly fast and reliable, but it demands specialized host bus adapters, specialized switches, and completely dedicated cabling.
Right, it represents a massive separate capital expense.
Exactly. NVMe over TCP changes that financial equation entirely. It takes those exact same high-speed NVMe storage commands and securely encapsulates them within standard TCP routing packets.
Oh, wow. While it might have marginally higher latency than purely dedicated fiber channel, it allows organizations to deliver incredibly high storage performance over the standard, widely available Ethernet networks they have already built.
Right. Networks they have already deployed and paid for, the cost-to-performance ratio is undeniable.
It is a brilliant way to maximize existing investments, but for all of these external protocols, cloud tiers, and storage efficiencies to actually function, the internal heartbeat of the storage cluster itself must be absolutely flawless.
This is a critical concept, yes.
We are going to dive just as deep into this final topic as the rest of the exam questions. The exam asks, in an ONTAP high availability pair, what is the primary role of the cluster interconnect?
And the distractors will suggest it connects the system to the public internet, or maybe that it provides power to the external disk shelves.
Right.
But the correct answer is C.
Right. The correct answer is C, to facilitate data replication and health monitoring between the nodes.
Exactly.
I constantly look at the cluster interconnect exactly like the corpus callosum inside the human brain.
The corpus callosum, okay.
Yeah, it is that thick, high-speed neural pathway connecting the left and right hemispheres. It allows the two halves to share complex operational information instantly and seamlessly.
So the physical body acts as one unified, coordinated organism rather than two separate, disjointed entities.
Exactly.
That is a profound way to conceptualize high availability architecture. Because if we rigidly break down the internal mechanics of an ONTAP system, the cluster interconnect is the absolute operational lifeline of the entire cluster.
It is a dedicated, highly specialized, ultra-high-speed network link, right?
Yes, and it is completely physically and logically isolated from any client data traffic or administrative management traffic. It exists exclusively for internal node-to-node communication.
Okay, so what is its most critical mechanical function then?
Mirroring write operations. When a host server writes data to Node A immediately uses the cluster interconnect to copy that exact data payload into the NVRAM of Node B.
Wait, it does this before it even acknowledges a successful write back to the host server?
Absolutely. Simultaneously, the interconnect is exchanging continuous, sub-second heartbeat signals and health statuses between the controllers.
Ah, so this continuous replication and monitoring ensures that if a catastrophic hardware failure occurs on Node A, the takeover process is completely seamless.
Exactly. Node B already possesses the mirrored data in its memory.
Mm.
It knows exactly what operational state Node A was in, and it can instantly assume full control without any data loss or disruption to the client applications.
Wow, that is a fascinating frontier to consider. Thank you so much for joining us on this deep dive. Keep asking hard questions, keep studying the underlying mechanics of these systems, and we will catch you next time.